Researchers from MIT and Harvard Medical School have developed a biocompatible and highly stretchable optical fiber made from hydrogel, an elastic rubbery material composed mostly of water. This bendable fiber may one day be implanted in the body to deliver therapeutic pulses of light or light up at the first sign of disease. The researchers say the fiber may serve as a long-lasting implant that would bend and twist with the body without breaking down. The team has published its results online in the journal Advanced Materials. Using light to activate cells and particularly neurons in the brain is a highly active field known as optogenetics, in which researchers deliver short pulses of light to targeted tissues using needle-like fibers, through which they shine light from an LED source. But the brain is like a bowl of jello, whereas these fibers are like glass, very rigid, which can possibly damage brain tissues. If these fibers could match the flexibility and softness of the brain, they could provide long-term more effective stimulation and therapy. The researchers tested the optical fiber's ability to propagate light by shining a laser through fibers of various lengths. Each fiber transmitted light without significant attenuation or fading. They also found that fibers could be stretched over 7 times their original length without breaking. Now that they had developed a highly flexible and robust optical fiber made from a hydrogel material that was also biocompatible, the researchers began to play with the fiber's optical properties to see if they could design a fiber that could sense when and where it was being stretched. They first loaded a fiber with red, green and blue organic dyes placed at specific spots along the fiber's length. Next, they shone a laser through the fiber and stretched, for instance, the red region. They measured the spectrum of light that made it all the way through the fiber and noted the intensity of the red light. They reasoned that this intensity relates directly to the amount of light absorbed by the red dye as a result of that region being stretched. In other words, by measuring the amount of light at the far end of the fiber, the researchers can quantitatively determine where and by how much a fiber was stretched. The researchers imagined that such stretchable strain-sensing optical fibers could be implanted or fitted along the length of a patient's arm or leg to monitor for signs of improving mobility.